When I was a kid, I always wanted to know, how do computers add numbers so seamlessly? So, like any curious kid would do, I did a little bit of internet research and I realized that using these basic logic gates, you can easily make an adder. And there's thousands of videos about how do computers add, and they're actually very informational and very good. I do like those videos, but how do computers multiply? It's more of a niche topic and it's not talked about as much. But in this video, we're going to understand how computers can multiply and how we can make a basic logic gate multiplier. So there's three ways that I found that computers can multiply, three different strategies, and we're going to explore each of them in this video. This is version 1 of how to make a multiplier. And this is kind of my own variation of how to do it. It's very simple actually. So if we go into Blender, and I'm going to draw this little animation up, but the way we multiply with numerical numbers in elementary was you multiply the ones by the top number, and then you add that to the multiplication of the tens also. So you know what I mean? So let's say we have the number 12 times 12, which is 144. So 2 times 2 is 4. 2 times 1 is 2, 24. And then we have to add that to 10 times 12, which is 120. And that will give us 144. So in the binary world, it's almost the exact same way. So if we multiply 12 times 12 in binary, we just have to add the place value digit for every digit that goes over 2 instead of the digits that go over 10 in our base 10 system. So if we add it up or multiply 12 times 12 real quick, this is what the math will look like, and this is how we're going to exactly do it in our simulation. So now if we go back to our simulation, this is what we have. So we can get this 3-digit number times this 4-digit number, and it works the exact same way. So we have these registers that are going to store and hold our numbers, and then we're going to use these adders to multiply the tens place, or to add the tens place, excuse me, by the ones place once we multiply the numbers. So for example, let's say we have 4 times 4. That gives us 16. You know, we have the 1s, 2s, 4s, 8, 16. Easy. We can do 6 times 6, which is 36. So we have the 1s, 2s, 4s, 8s, 16, 32. So 32 plus 4 is 36. And it works very well actually, and I'm very proud of this little circuit right here. And if we look a little closer at the circuit, so just like how we have to add the placeholder for every binary digit, over 2, it's represented perfectly right here. So this is the binary digit 1. Let's see. It goes up to this first register, and we go exactly into this 1's place value in the adder. And then 2 goes up to the second register, and we skip the first one almost to like mimic a 0 being stored, and then we just go into the next bit of the adder. So we skip the 1 of the adder and go up, almost like a 0 placeholder was there. And then we do the same with the other 2. We have this 2 placeholder spot, and then we have this 3 placeholder spot for the top one. And then we add these numbers up, and there we go. We have a little multiplier right here. So the second way we can multiply is a little more complicated. So let's see if I can pull this up real quick. And that is through just repeated addition of a computer. And this way is a little more impractical. I guess it can save on transistor count, but your code will have to be longer. But since modern transistors are so small, you can just put a multiplying unit in your computer in order to multiply within 1 clock cycle instead of 4. But I mean, the way you would do it is pretty simple. You would store a number in the register, add the number, and then like just repeat it for however many times. Yeah, actually I'm not going to show y'all real quick because it's very, very self-explanatory how this would work. And then the third way that computers would multiply was an interesting method developed in the 1970s. And that was using logarithms. And this way is really, really complicated. So I'm not going to fully explain it really in this video at all. If y'all want to, I'll make a future video probably explaining how it, but it is super complicated. Yet it did save on transistor count, especially in the early 1970s. So that's why they implemented it, because you could multiply very large numbers using this method relatively quickly. But since that is not in our interest right now, because we're just building a very basic computer, we don't need to multiply very large numbers. So we're going to use method 1 that I have shown in this video. But I just want to let y'all know that this does exist, and it was a solution on how to multiply when in early computer technology. So that's it for this episode of Folzor, where we explored the multiplication logic gate system that allows computers to multiply. And besides like the obvious fact of why computers need to multiply, especially for like calculators and calculations, another fact is that's how AI works. So AI is all based on inputs and weights to make a neural network. And you need to multiply the weights by constants and other numbers to get the correct output. So multiplication is crucial for AI to work, which we will 100% explore in another video, because AI is about to take over the world. So we need to know how this works. But thank you for watching, and I'll try to post more frequently because the channel is growing. So let's see if I can do 2 times a week this week. So come back Thursday for another video. Thank you.